A single explosion outshines every star in its galaxy combined. These are the universe's most energetic events, cosmic powerhouses that forge the elements of life and sculpt the very shape of galaxies. You are about to embark on a journey through 50 incredible facts that reveal the violent beauty of supernova, hypernova, and beyond. We will uncover how a star's death seeds new worlds and confront the mystery of bursts so powerful they could threaten a planet from across the cosmos. By the end, you will see the night sky not as a static picture, but as a dynamic arena of creation and destruction. What hidden force do you think drives these magnificent celestial fireworks? The sheer violence of these events is almost impossible to comprehend. To even begin, we must first define what makes an explosion in space truly energetic. It is not merely a bright flash, it is a star tearing itself apart, releasing more energy in a single instant than our Sun will produce over its entire 10 billion-year lifetime. This energy does not take just one form. It erupts as a blistering wave of light across every wavelength, from radio waves to lethal gamma rays. It hurls matter outward at nearly the speed of light, a kinetic blast that can sweep up interstellar gas for thousands of years. And in the most extreme cases, it shakes the very fabric of spacetime, sending out ripples we call gravitational waves. This is a fundamentally different class of event from a solar flare or a stellar outburst. Those are surface tantrums. What we are exploring are terminal, core-deep catastrophes that mark the end of one cosmic era and the violent, brilliant birth of another. The most common engine for these cosmic blasts is the supernova, a star's final, magnificent death cry. Not all stars die this way, only the true giants, those born with at least 8 times the mass of our own Sun. Their entire lives are a desperate battle against gravity, and a supernova is the moment they ultimately lose. This collapse happens in 2 primary, spectacularly violent ways. The first is the core collapse supernova. For millions of years, a massive star fuses elements in its core, first hydrogen, then helium, creating a layered onion of increasingly heavier atoms. This process continues until the core is solid iron, but iron is a stellar poison. Fusing iron does not release energy, it consumes it. With its energy source cut off, the core can no longer support its own immense weight. In less than a second, it collapses from a sphere the size of Earth down to a city-sized ball of neutrons. The outer layers of the star, suddenly with nothing to support them, come crashing down at a quarter of the speed of light. They hit the new, impossibly dense neutron core and rebound in the most powerful shockwave the universe can produce, blowing the entire star apart. The second type involves the dead cores of smaller stars called white dwarfs. If a white dwarf orbits close to a companion star, it can slowly steal material. This theft pushes the white dwarf closer and closer to a critical mass. When it reaches a point called the Chandrasekhar limit, a runaway thermonuclear explosion tears through its entire carbon and oxygen body in a matter of seconds. It is a stellar bomb of unimaginable scale, leaving nothing behind. In both cases, the result is the same. For a few glorious weeks, that single dying star can shine brighter than every other star in its galaxy combined. It is a fleeting, brilliant funeral pyre that scatters the elements forged in its heart and violent death across the cosmos. This stardust, this cosmic fertilizer, will one day form new stars, planets, and even life itself. This brilliant funeral pyre is not a single, uniform event. Astronomers have learned to read the light from these explosions like a forensic report, classifying them into distinct types that reveal the star's original identity and the precise mechanics of its death. The primary split is between Type 1 and Type 2 supernova. The key difference lies in their light signatures. When we break down a supernova's light into a spectrum, we see specific colors missing, absorbed by different elements in the expanding debris. Type 2 supernova show a clear fingerprint of hydrogen in their spectra. This tells us the exploding star was a true giant, one that held onto its outer hydrogen envelope until its final moment. This is the classic core collapse death we described earlier. Within this type, we see further variations like Type 2P supernova, which exhibit a peculiar plateau in their light curve, meaning their brightness remains steady for months before fading, a sign of a particularly massive hydrogen-rich envelope. Then we have the Type 1 supernova, which lack any hydrogen signature at all. This absence is just as telling. It means the star had already lost its outer layers before it exploded. This category splits into three fascinating subclasses. Type 1, a supernova, come from the thermonuclear detonation of a white dwarf. They are the most important for cosmology because they are remarkably consistent. Since they all explode at nearly the same critical mass, they all reach nearly the same peak brightness. This makes them perfect standard candles, cosmic mileposts that allow us to measure vast distances across the universe. Type 1b and 1c supernova, however, are core collapse events of massive stars that have been stripped of their hydrogen. A Type 1b still shows helium in its spectrum, while a Type 1c has lost both its hydrogen and helium, exposing deeper, heavier elements. These are the deaths of stars ripped apart by powerful stellar winds or by a companion star. So, from a simple flash of light in the darkness, we can deduce the star's life story, its mass, its companions, and the very physics that tore it asunder. That critical moment of stellar death hinges on a single element, iron. Deep within the core of a massive star, a relentless nuclear furnace has been burning for millions of years. It fuses lighter elements into heavier ones, a process that releases the energy which has kept the star shining, and more importantly, kept it from collapsing under its own immense gravity. First, hydrogen fuses into helium, then helium into carbon and oxygen, building up layers like a cosmic onion. Each new fuel source burns hotter and faster than the last. This continues until the core is primarily silicon. In a final, frantic blaze lasting less than a day, the silicon fuses, creating the star's ultimate ash iron. And here lies the catastrophe. Up to this point, every fusion reaction released energy, propping up the star against gravity. But iron is different. Fusing iron atoms together does not release energy, it consumes it. It is a nuclear dead end. Suddenly, the star's central engine shuts off. With no outward pressure from fusion to support it, the iron core cannot withstand its own weight. In a fraction of a second, gravity wins its ancient battle. The core, which was once a sphere roughly the size of Earth, implodes catastrophically. It collapses at speeds approaching 1/4 the speed of light, crushing down into an impossibly dense ball of neutrons no larger than a city. The outer layers of the star, with nothing left to stand on, plummet inward after it, but they do not quietly join the core. They slam into this newly formed, ultra-hard neutron surface with unimaginable force. The inward-falling material rebounds, creating the most powerful shock wave in the known universe. This rebounding shock, amplified by a flood of neutrinos pouring out from the newborn core, violently reverses the collapse. It ripples outward, tearing the entire star apart from the inside out in a brilliant supernova explosion. This is the stellar death that forges life. The incredible energy of that blast is what fuses elements heavier than iron, like gold, silver, and uranium, and then hurls them out into the galaxy. Every piece of jewelry, every electronic component, the very iodine in your body, was once forged in such a violent stellar death. That iron core, crushed down to the size of a city, does not simply vanish. In the chaotic aftermath of the supernova blast, this remnant often survives as one of the universe's most bizarre objects, a neutron star. Picture the entire mass of our Sun, but compressed into a perfect sphere only about 12 miles across. The density this creates is beyond human comprehension. A single teaspoon of neutron star material would weigh not millions but billions of tons on Earth. It is essentially a giant atomic nucleus, a solid ball of neutrons. This incredible state of matter is only possible because of a fundamental quantum law known as the Pauli exclusion principle. This principle states that two identical particles cannot occupy the same quantum state. In the collapsing core, electrons are forced into atomic nuclei, combining with protons to form neutrons. Soon, the entire core is a sea of neutrons, all pressed shoulder to shoulder. They resist being squeezed any closer, not through heat or chemical bonds, but through this degeneracy pressure, a final, fundamental refusal to violate the rules of quantum physics. This pressure is what permanently halts the collapse, saving the core from becoming a black hole and creating a stable, yet utterly alien, world. Some of these neutron stars reveal themselves as pulsars. If the original star was spinning, its collapse speeds it up dramatically, just as an ice skater spins faster when they pull their arms in. A newborn neutron star can rotate hundreds of times per second. As it spins, it beams intense radiation from its magnetic poles. If one of these beams sweeps across Earth, we detect a regular pulse of energy, a cosmic lighthouse blinking with metronomic precision. These pulsating signals were so regular when first discovered that astronomers briefly entertained the idea they might be signs of an advanced civilization. The reality is almost as strange, a stellar corpse spinning faster than a kitchen blender, a permanent monument to the star that died to create it. The precision of these spinning stellar corpses is so absolute it was once mistaken for a message. When a neutron star is born with a powerful magnetic field and a rapid rotation, it becomes a pulsar. Picture its magnetic poles not aligned with its axis of spin. From these poles, intense beams of radio waves, light, and even X-rays shoot out into space. As the star rotates, these beams sweep across the cosmos like the beacon of a galactic lighthouse. If our planet happens to lie within the path of one of these sweeping beams, we detect a regular, repeating pulse of energy. The timing of these pulses is astonishingly reliable, some ticking with a stability that rivals atomic clocks. This very reliability led to one of astronomy's most charming mysteries. In 1967, a graduate student named Jocelyn Bell Burnell was analyzing data from a new radio telescope when she noticed a peculiar repeating signal. It was a series of sharp pulses arriving every 1.337 seconds with unbelievable regularity. The signal was so perfect, so artificial seeming, that a team half-jokingly labeled it LGM-1 for little green men. They genuinely considered the possibility that they were detecting a beacon from an advanced extraterrestrial civilization. Of course, the true explanation was far more extraordinary. They had discovered the first pulsar, the spinning remnant of a long-dead star. This cosmic metronome was not a greeting from aliens, but a natural phenomenon of almost unbelievable physics, a city-sized ball of neutrons spinning faster than a helicopter rotor, broadcasting its existence across the light years. But the universe can forge something even more terrifying than a simple pulsar. From the crucible of a supernova, a special kind of neutron star can be born, one with a magnetic field of almost incomprehensible power. These are magnetars. To grasp their strength, consider the most powerful magnet you have ever encountered, perhaps one that can lift a paperclip. Now, imagine a magnetic field 1 quadrillion times stronger than the one that surrounds our entire planet. This is the ferocious magnetism of a magnetar. It is so intense that it warps the very structure of matter itself, creating a crystalline crust on the star's surface. This crust is under unimaginable stress, and like the tectonic plates on Earth, it can crack. When it does, the event is called a starquake. The energy released is apocalyptic. The entire star shudders, realigning its magnetic field in a fraction of a second, and unleashing a flash of gamma rays and X-rays so brilliant it can outshine every star in the Milky Way for a fleeting moment. These bursts are short-lived, often lasting less than a second, but in that blink of an eye, a magnetar becomes the most magnetic object we have ever discovered, a true cosmic powerhouse lurking in the debris of a dead star. Yet even the ferocious power of a magnetar pales beside a far grander cataclysm. For the most massive stars in the cosmos, death is not a supernova but a hypernova. This is the ultimate stellar explosion, an event so energetic it makes a standard supernova look like a firecracker. These events are born from stars that begin their lives with at least 30 times the mass of our Sun. Their fate is not to form a neutron star but to undergo a complete and total collapse. The core, once it forms iron, does not stabilize. There is no rebounding shockwave strong enough to save it. Instead, the entire stellar core plunges inward, not stopping at a city-sized ball of neutrons, but continuing its catastrophic fall until it forms a black hole. This direct collapse model gives the hypernova its other name, a collapsar, but the formation of the black hole is only the beginning of the violence. As the outer layers of the star rush inward, they don't just vanish. They form a superheated, swirling disk of debris, an accretion disk spiraling around the newborn black hole at nearly the speed of light. The immense magnetic fields and rotational energy of this system then focus and channel some of the infalling material. This material is blasted outward from the poles of the collapsing star in two narrow, unimaginably powerful jets. These are not gentle streams of gas. They are beams of plasma moving at over 99.9% of the speed of light, making them relativistic jets. It is these jets drilling their way out through the body of the dying star that we see from across the universe. When one of these jets is pointed directly at Earth, we witness the single most luminous electromagnetic event known to exist, a long-duration gamma-ray burst. For up to a minute, this narrow beam can outshine every other gamma-ray source in the entire cosmos combined, a fleeting, deadly spotlight from a star turning itself inside out to birth a monster. These jets from hypernova are the source of the universe's most powerful beacons. We call them gamma-ray bursts. A single one of these events is the most energetic electromagnetic explosion known to exist. In just a few seconds, a typical gamma-ray burst can release more energy than our Sun will emit across its entire 10 billion-year lifespan. It is a flash of pure, concentrated violence that can outshine every other source of gamma rays in the cosmos combined. The story of their discovery is almost as incredible as the bursts themselves. It begins not with astronomers, but with the United States Air Force. During the Cold War, the United States launched a series of satellites named Vela, designed to monitor the globe for secret nuclear weapons tests which were banned by treaty. These satellites were equipped with sensors to detect the telltale flash of gamma radiation from a nuclear detonation in Earth's atmosphere or in space. They worked perfectly, but they began picking up something completely unexpected. The sensors were triggered by brief, intense bursts of gamma rays that were clearly not coming from Earth. They originated from deep space, appearing randomly from all directions across the sky. The data was classified for years, a military secret that puzzled scientists. When the findings were finally declassified, the astronomical community was stunned. No one could explain what natural phenomenon could possibly produce such titanic, fleeting blasts of the highest energy light. For decades, their true origin remained one of the greatest mysteries in astrophysics. The key to understanding these cosmic flashes lies in their duration. Astronomers quickly realized that gamma-ray bursts are not all the same. They fall into two distinct classes, separated by a simple but profound dividing line of just 2 seconds. On one side are the long-duration gamma-ray bursts. These events last anywhere from 2 seconds to several minutes, and we now know they are the final death cries of the most massive stars in the universe. Each long burst is the signature of a hypernova, a star collapsing directly into a black hole and firing off those twin, ultra-relativistic jets. If one of those jets is pointed at us, we see the brilliant, long-lived gamma-ray flash. But what about bursts that are far briefer? The other class is the short-duration gamma-ray burst. These events are incredibly fleeting, lasting less than 2 seconds and often just a few hundred milliseconds. They are the universe's quickest and most powerful flashes. For years, their origin was a deeper mystery than that of their longer cousins. A massive star cannot collapse that quickly. The engine for a short burst had to be something entirely different, something that could unleash a titanic blast of energy in the blink of an eye. The leading theory points to the most violent mergers in the cosmos. Imagine two neutron stars, each a city-sized ball of ultra-dense matter, locked in a final, deadly dance. They spiral inward for millennia, radiating energy as gravitational waves until they finally collide. In that catastrophic impact, a portion of their material is squeezed and shredded, forming a black hole almost instantly and launching its own set of narrow, energetic jets. This entire cataclysm, from collision to jet formation, happens in a fraction of a second, producing the short, sharp burst of gamma rays we detect. Alternatively, a neutron star merging with a black hole can create a similar, fleeting flash. So, from a simple timer, we can decipher the entire story behind the explosion. A long burst tells a tale of a single, monstrous star's death. A short burst whispers the story of two dead stars finding a violent end together. The true power of a gamma-ray burst is not in a sphere of light, but in a focused blade. This energy is channeled into two narrow beams known as relativistic jets that erupt from the poles of the dying system. The engine for these jets is a cosmic monster, either a newborn black hole or an intensely magnetic magnetar. As material swirls down toward this central object in a superheated accretion disk, the incredible rotational energy and magnetic fields act like a cosmic particle accelerator. They grab a fraction of the infalling matter and fling it outward along the axis of rotation. These are not gentle outflows. The material in these jets is accelerated to over 99.99% of the speed of light. At these velocities, the laws of relativity take over, concentrating the energy into an incredibly tight beam. This is the secret to the burst's unbelievable luminosity. All that catastrophic power is not spread in all directions, but focused into a pair of searchlights, and this leads to a profound conclusion about our own view of the cosmos. We only detect a gamma-ray burst if our planet happens to lie directly within the path of one of these deadly beams. For every brilliant flash we see, there are hundreds of similar stellar cataclysms happening in galaxies across the universe, their jets pointing harmlessly off into empty space. We are merely catching the fleeting, terrifying glare of a cosmic lighthouse as its beam sweeps across our tiny world. That brilliant initial flash is only the beginning of the story. Once the gamma-ray burst itself fades, often in less than a minute, it leaves behind a fading cosmic fingerprint known as the afterglow. This is not a single color of light, but a cascade of radiation that shifts across the electromagnetic spectrum over days or even weeks. The initial relativistic jet, having blasted its way out of the star, begins to plow into the tenuous gas of interstellar space. This collision is not a gentle one. The jet, moving at almost the speed of light, slams into this material, creating a powerful shockwave. This shockwave acts like a giant natural particle accelerator, causing the gas to glow intensely. First, it emits X-rays, which can be detected by orbiting observatories for several days. Then, as the shockwave slows and expands, the emission shifts down in energy to optical light, the kind our eyes can see. For a brief time, this makes the burst's location visible through a powerful telescope as a new, fading star in a distant galaxy. Finally, the emission reaches radio frequencies where the faint remnants of the event can be studied for weeks. This multi-wavelength afterglow is the key that unlocked the greatest mystery of gamma-ray bursts, their distance. Before its discovery, we had no idea if these bursts were happening in our own galactic backyard or at the edge of the observable universe. The afterglow allows astronomers to point their most powerful telescopes at the exact spot in the sky and capture a spectrum of its light. By analyzing this spectrum, they can measure the redshift, a stretching of light waves caused by the expansion of the universe. The greater the redshift, the farther away the object is. It was through this method that astronomers made a stunning discovery in the late 1990s. Gamma-ray bursts were not local, they were occurring in galaxies billions of light-years away. This meant the energy required to make them visible from such an immense distance was almost beyond comprehension, confirming they were the most powerful explosions since the Big Bang itself. The sheer distance of these cosmic explosions is our greatest protection. But what if that were not the case? Let us consider a terrifying possibility. A gamma-ray burst occurring not in a galaxy billions of light-years away, but right here in our own cosmic neighborhood. If a long-duration gamma-ray burst were to happen within a few thousand light-years of Earth, and if its deadly relativistic jet were pointed directly at us, the consequences would be catastrophic. The initial blast of gamma radiation would not be a harmless flash in the sky. It would deliver a direct, concentrated energy strike to our planet's atmosphere. This high-energy assault would break apart nitrogen and oxygen molecules, initiating a complex chemical chain reaction. The result would be the creation of vast quantities of nitrogen dioxide, a brownish gas that acts like a smog, blocking sunlight and causing rapid global cooling. More critically, this chemical process would devastate our planet's ozone layer. This protective shield, which filters out the sun's harmful ultraviolet radiation, could be depleted by 50% or more. It would take years, perhaps even a decade, for the ozone to recover. In that time, the surface of our world would be bathed in lethal levels of ultraviolet light. This would trigger a mass extinction event, devastating the base of the food chain by killing off phytoplankton in the oceans and causing widespread crop failures and mutations on land. The event would be a direct astronomical cause of a planetary die-off. Now, before this thought keeps you awake at night, you must hear the crucial reassurances. The probability of such a direct hit is astronomically low. For it to happen, a very specific, extremely massive star would need to be both close enough and oriented with its polar jet aimed right at us. The types of stars that produce these hypernovae are rare, and their jets are incredibly narrow. The vast majority of such events in our galaxy would have their beams pointing harmlessly in other directions. Furthermore, there are no candidate stars known to be in the right stage of their life and close enough to pose any imminent threat. This hypothetical scenario, while frightening, serves a different purpose. It is the ultimate demonstration of the raw, untamed power of these stellar explosions. A single event happening from a distance that is still cosmically next door could fundamentally alter the biology of an entire world. It forces us to recognize that we live in a dynamic and sometimes violent universe where the death of a distant sun can have consequences that echo across light years. While a hypernova creates a black hole, the merger of two neutron stars forges a different kind of treasure. These collisions produce a kilonova, an explosion that is actually far less energetic than a supernova. But what it lacks in raw power, it more than makes up for in cosmic significance. A kilonova is the universe's primary factory for the heaviest elements. In the heart of this chaotic merger, conditions become unimaginably extreme. The two neutron stars tear each other apart, spraying a dense cloud of neutrons into space. This process, known as rapid neutron capture, allows atomic nuclei to gorge themselves on free neutrons, building up elements far heavier than iron in a matter of seconds. It is here, in this brief, violent event, that most of the universe's gold, platinum, and uranium are created. For a long time, this was just a compelling theory. Then, in August of 2017, a new era of astronomy dawned. gravitational wave observatories detected ripples in spacetime from an event called GW 170817. Just seconds later, telescopes across the globe and in space saw a corresponding flash of light from the same patch of sky. For the first time in history, we had witnessed a kilonova in both gravitational waves and light. The data was a perfect match, confirming that the collision of two neutron stars had indeed seeded a distant galaxy with a fortune in heavy elements. The gold in your ring, the platinum in a catalytic converter, were likely born in such a cataclysmic dance of dead stars. That detection in 2017 was a symphony of cosmic signals. For the first time, we did not just see the universe, we also heard it. The LIGO Observatory in the United States and its European partner Virgo are not telescopes in any traditional sense. They are immense listening posts for the fabric of reality itself. Each consists of laser beams traveling down multi-kilometer long tunnels arranged in an L shape. When a gravitational wave, a ripple in space-time generated by a massive collision, passes through Earth, it minutely stretches one arm of the L while squeezing the other. This tiny distortion, smaller than the width of a proton, changes the laser light's travel time. On August 17, 2017, these instruments sensed a distinctive chirp, a rising ripple that lasted for about 100 seconds. This was the sound of two neutron stars locked in a final, decaying orbit, spiraling together over 30 million light-years away. The signal's character was unmistakable, the fingerprint of a binary neutron-star merger. But the true revolution was just beginning. Within 2 seconds of the gravitational wave detection, orbiting satellites caught a short gamma-ray burst from the same region of sky. The gravitational wave signal had provided the direction, and now the gamma-ray flash confirmed the cataclysm. Astronomers around the world were alerted, and they swung every available telescope toward that single point. What they witnessed was the predicted kilonova, a glow of light across all wavelengths that faded over days, its color shifting from blue to red as heavy elements formed and decayed in the expanding debris. This was the birth of multi-messenger astronomy. We had felt the space-time shake, seen the initial flash, and then watched the fallout, all from the same event. This single observation confirmed decades of theory, proving that the cosmic forges for gold, platinum, and other heavy elements are indeed the violent mergers of these dead stars. But there is a theoretical fate for stars so massive it defies even the hypernova. Picture a stellar behemoth born with more than 130 times the mass of our Sun. Its life is a frantic race, burning through its nuclear fuel at a staggering rate. Deep in its core, the temperature soars to an almost inconceivable level, over 1 billion degrees. At this extreme inferno, something strange happens to the very nature of light. Photons, the particles of light that provide the radiation pressure holding the star up, suddenly become powerful enough to spawn matter. They spontaneously transform into pairs of electrons and their antimatter counterparts, positrons. This process is a catastrophe for the star. Light, which was providing outward pressure, is now being converted into these particle pairs. But this new matter does not provide the same supportive force. It is as if the supporting pillars in a burning building were suddenly turned into sand. The core loses its pressure almost instantly. Without that support, gravity wins in a single, violent surge. The core begins to collapse, heating up even further and triggering runaway nuclear fusion. But this is not a collapse that forms a neutron star or a black hole. The entire star, from core to surface, undergoes a complete thermonuclear detonation. The explosion is so utterly total that it blasts the star to smithereens, leaving nothing behind, not even a remnant. This is a pair instability supernova, a theoretical explosion of pure annihilation that would be one of the most powerful events in the universe, a final, complete dissolution of a star into stardust and light. That theoretical limit of stellar violence was thought to be unimaginably high, but in 2015, our instruments recorded something that should not have been possible. Designated Assassin 15LH, this cosmic explosion was spotted by a network of small, automated telescopes designed to scan the entire sky for new transient events. When the data came in, astronomers were stunned. At its peak, this single object shone with a luminosity of roughly 570 billion times that of our Sun. It was more than twice as bright as any supernova ever recorded, outshining our entire Milky Way galaxy by a factor of 20. This was not just a new record, it was an event that shattered our existing categories for stellar explosions. The immediate question was, what kind of cosmic engine could possibly produce such a sustained, phenomenal output of pure light? The first and most exciting hypothesis pointed toward the ultimate stellar death, a pair instability supernova. A star would need to be a true monster, perhaps 200 times the mass of our Sun, to undergo such a complete and violent self-annihilation. The energy released in a pair instability event is theoretically sufficient to explain the staggering brightness of Assassin 15LH. It would be the death of a primordial giant, a type of star thought to have existed only in the early universe. Yet, as more data was collected, the story grew more complex. Observations from the Hubble Space Telescope revealed something peculiar. The explosion had occurred not in a star-forming region where such massive stars are born, but in the quiet, aging heart of a large red galaxy. This is exactly the kind of environment where you would expect to find a different kind of monster, a supermassive black hole. This led to a second, equally compelling theory. Perhaps Assassin 15LH was not a supernova at all. Maybe it was the signature of a star that wandered too close to a rapidly spinning, supermassive black hole. In this scenario, the black hole's immense tidal forces would stretch and shred the star in a process called tidal disruption. The stellar debris would then spiral into a brilliant, hot accretion disk around the black hole, flaring with a light that could easily rival the most powerful supernova. The intense, sustained brightness could be explained by the slow and steady consumption of a star, rather than a single, instantaneous blast. To this day, the true nature of Assassin 15LH remains an active and passionate debate among astronomers. It is a powerful reminder that our catalogue of cosmic explosions is far from complete. The universe continues to surprise us, presenting events that defy our neat classifications and force us to reconsider the very limits of power in the cosmos. Even black holes can create their own version of a stellar explosion. When a star drifts into the fatal embrace of a supermassive black hole, it experiences a death unlike any other, a tidal disruption event. The star is not torn apart by an internal collapse, but shredded by an external force of unimaginable power. This is the work of tidal forces, a difference in gravity so extreme it overcomes the star's own self-gravity. The side of the star closest to the black hole feels a vastly stronger gravitational pull than the side facing away. This difference stretches the star horizontally while compressing it vertically, pulling it apart like taffy into a long, thin stream of superheated gas. Roughly half of this stellar debris is flung away into the darkness, while the other half is captured by the black hole's gravity. This material does not fall straight in. It forms a vast, swirling accretion disk around the event horizon, a maelstrom of plasma heated to millions of degrees through friction and violent collisions. As this matter spirals inward, it releases a tremendous flare of radiation, a brilliant flash of light that can outshine every star in the galaxy's core for months or even years. This is not a supernova, but a gravity-powered explosion, a final, spectacular feast for a cosmic monster. Even the steady glow of a black hole's feast can sometimes flicker with a strange, cosmic rhythm. Astronomers have recently identified a bizarre new class of explosion called a quasi-periodic eruption. These are not one-time cataclysms, but a series of repeating X-ray bursts emanating from the accretion disks of supermassive black holes. Picture a distant galaxy, its core harboring a monster millions of times heavier than our Sun. Instead of a constant, brilliant flare from its consumption of gas, this core suddenly pulses. It unleashes a sharp burst of high-energy X-rays, then falls quiet, only to erupt again an hour or so later. This cycle repeats over and over, a regular, ticking time bomb of energy hidden in the heart of a galaxy. The timescale is what makes it so puzzling. An hour is far too long for it to be related to the final moments of a single star falling in, and far too short to be linked to any large-scale changes in the disk itself. It is as if something within the black hole's immediate, violent neighborhood is switching on and off with the regularity of a cosmic metronome. The leading theories are as fascinating as the phenomenon itself. One idea suggests a second, smaller black hole might be orbiting the supermassive one. As this smaller object plows through the outer edges of the accretion disk on its elliptical path, it could be scooping up gas and triggering a burst of X-rays with every close pass. Another possibility involves instability within the disk itself, where magnetic fields build up to a breaking point, releasing their energy in a periodic flash before the process begins anew. Whatever the cause, these quasi-periodic eruptions are a stark reminder that the environments around black holes are not just chaotic voids. They can possess a hidden, almost musical structure, a rhythmic drumbeat of pure energy whose source remains one of the most compelling new mysteries in high-energy astrophysics. Not every stellar explosion marks a final death. Some are brilliant surface tantrums, cosmic fireworks that can repeat again and again. These are nova, the smaller but still spectacular cousins of supernova. The stage for a nova is always a binary star system where two stars are locked in a close gravitational dance. One star is a white dwarf, the dense, Earth-sized core of a star that has already died a quiet death. Its partner is often a main sequence star like our Sun or a bloated red giant. The white dwarf's intense gravity acts like a cosmic vacuum, relentlessly pulling hydrogen-rich gas from the outer layers of its companion. This stolen material doesn't just fall onto the white dwarf's surface. It forms a swirling, superheated disk of gas that slowly spirals inward, eventually settling onto the white dwarf itself. Over thousands of years, this hydrogen builds up into a dense, pressurized layer on the surface of the degenerate star. The pressure and temperature at the base of this hydrogen ocean climb to a critical point. Suddenly, the conditions become perfect for nuclear fusion, but in a runaway, explosive manner. This is not the steady fusion of a star's core. It is a titanic thermonuclear blast that ignites the entire accumulated layer at once. The white dwarf's surface is engulfed in a cataclysmic detonation, blasting the unburned outer portion of the hydrogen shell into space at speeds of thousands of kilometers per second. For a brief period, this single point in the sky can increase in brightness by 50,000 to 100,000 times, outshining entire constellations. Yet the white dwarf itself remains completely intact. It survives the blast, and almost immediately, it begins the process all over again, pulling in fresh fuel from its companion. This is the crucial difference between a nova and a supernova. A supernova is a star's final, core-deep self-destruction. A nova is a surface-level hydrogen bomb that leaves the underlying star ready to repeat the cycle. Some nova are even known to be recurrent, flashing brilliantly every few decades or centuries as they reach that same critical mass of stolen fuel, a regular reminder of the dynamic violence simmering in even the most seemingly stable stellar systems. RS Ophiuchi is a ticking clock in the constellation of Ophiuchus. Roughly every 2 decades, this binary star system erupts into a brilliant nova, a cycle astronomers have observed for over a century. Each explosion is a perfect natural laboratory. Because we know another eruption is imminent, we can have telescopes from radio to X-ray trained on the system beforehand, ready to capture the entire event from the first flicker to the final fade. This repeated observation reveals the intricate physics of the blast in a way a one-time event never could. We see the shockwave from the explosion plowing through the stellar wind left by the system's red giant star. We measure how much material is ejected and how much falls back, but this beautiful regularity hints at a far more violent future. With every cycle, the white dwarf is not just expelling material, it is also stealing it. While most of the accumulated hydrogen is blasted away, a tiny fraction of that stolen mass may be compressed into the white dwarf's core, permanently increasing its weight. Over thousands of cycles, this slow accumulation pushes the white dwarf closer and closer to the Chandrasekhar limit, that critical threshold of about 1.4 times the mass of our Sun. If it crosses that line, the entire star will no longer be able to support its own immense density. The result will not be another surface-level nova. It will be a runaway thermonuclear fusion that consumes the entire white dwarf in a matter of seconds, a cataclysmic type I supernova. RS Ophiuchi is not just a recurrent nova, it is a supernova in waiting, a patient cosmic bomb being slowly armed with each stellar theft. Our own Sun is a constant reminder that cosmic explosions are not just distant spectacles. While it is not massive enough to die in a supernova, it regularly unleashes its own brand of localized fury through solar flares and coronal mass ejections. A solar flare is a sudden, intense flash of radiation that erupts from the Sun's surface, a burst of energy equivalent to millions of 100-megaton nuclear bombs exploding simultaneously. This flash of X-rays and extreme ultraviolet radiation travels at the speed of light, reaching Earth in just over 8 minutes, but the light is only the first warning. Often accompanying a powerful flare is a far more massive, slower-moving event called a coronal mass ejection. This is not just a flash of light, but a physical eruption of the Sun itself. A CME hurls billions of tons of superheated plasma, a cloud of charged particles and magnetic fields, directly into space. If this colossal bubble is aimed at Earth, it takes anywhere from 1 to 3 days to cross the 93-million-mile gulf. When it arrives, the consequences are a double-edged sword of beauty and danger. The interaction of these charged particles with our planet's magnetic field creates the breathtaking auroras, the northern and southern lights, painting the polar skies with shimmering curtains of green and red. Yet, this same influx of solar energy can be deeply disruptive. It induces powerful electrical currents in the ground that can overload power grids, leading to widespread blackouts. It can fry the delicate electronics of satellites, crippling global communications and GPS networks. It even poses a radiation hazard for astronauts in orbit and pilots on high-latitude flights. So while our Sun provides the gentle light for life, it also holds the power, with a single well-aimed eruption, to throw our technologically dependent civilization back a century in a matter of hours. The most dramatic proof of solar power struck Earth in September 1859. It began with a brilliant white light flare observed by the astronomer Richard Carrington, a sudden conflagration on the surface of the Sun. What followed was a coronal mass ejection of unprecedented power, a storm of charged particles aimed directly at our planet. When it arrived just 18 hours later, the effects were both spectacular and terrifying. The global telegraph system, the Victorian era's internet, collapsed. Operators received severe electric shocks from their equipment, pylons threw sparks, and some telegraph papers spontaneously caught fire. Meanwhile, the night sky erupted in a celestial firestorm. Auroras, normally confined to the polar regions, blazed so brightly that people could read newspapers by their crimson and emerald light in the middle of the night. These phantom lights were seen as far south as Cuba and Hawaii, convincing many that the world was ending. The Carrington event was not a distant supernova or a gamma-ray burst, but a direct hit from our own life-giving star. It serves as a permanent warning, A storm of that magnitude today would be a global technological catastrophe, frying satellites, collapsing power grids, and plunging continents into darkness for months or even years. The universe's most energetic explosions are not always light years away. Sometimes the most immediate danger is the gentle star we see outside our window every single day. Our sun's occasional temper tantrums, however, are nothing compared to the rage of other stars. Across the galaxy, astronomers have documented the existence of superflares, eruptions that can be thousands, even millions of times more powerful than anything our sun has ever produced. These are not gentle reminders of solar activity, but cataclysmic events that can fundamentally reshape a star's entire planetary system. The Kepler Space Telescope, designed to hunt for planets, became an accidental superflare detective. By staring relentlessly at the same patch of sky, it watched for the tiny dips in starlight caused by a planet passing in front of its star, but sometimes the light curve would do the opposite. It would suddenly and dramatically spike. A star would, in a matter of hours, become significantly brighter. These were the superflares, titanic releases of magnetic energy that dwarf our own solar maximum. For a planet orbiting in the so-called habitable zone of one of these active stars, a superflare is not a light show. It is an existential threat. The initial blast of X-rays and ultraviolet radiation would be devastating, but the real danger comes from the coronal mass ejection that would almost certainly follow. Imagine a wave of charged particles so immense it could not just interact with an atmosphere, but strip it away entirely. The planetary magnetic field would be overwhelmed, the ozone layer obliterated. The surface would be bathed in lethal radiation, scouring it of any complex life. A single such event could turn a lush, Earth-like world into a sterile, irradiated rock. This discovery forces us to reconsider the very definition of a habitable world. It is not enough for a planet to be the right distance from its star for liquid water. It must also orbit a star with a stable, gentle disposition, a sun that provides light and warmth without periodically trying to erase the life it helped create. The ghost of a supernova still pulses with incredible energy. The Vela pulsar, born from a stellar collapse about 10,000 years ago, is a celestial lighthouse in more ways than one. While it famously blinks in radio waves, this spinning stellar corpse holds a far more energetic secret. It is one of the brightest persistent sources in the entire gamma-ray sky. This is not the brief, cataclysmic flash of a gamma-ray burst, but a constant, seething fury. The engine for this relentless glow is the pulsar wind. As the Vela pulsar spins, its immensely powerful magnetic field acts like a gigantic turbine, ripping charged particles from its surface and accelerating them to nearly the speed of light. This creates a gale of electrons and positrons that streams out into the surrounding space, a hurricane of pure power known as the pulsar wind nebula. When these ultra-relativistic particles slam into the slower-moving gas and magnetic fields of the nebula, they are whipped into a frenzy, forced to change direction violently. This sudden acceleration forces them to shed their immense kinetic energy, and they do so by emitting the highest energy photons in the universe, gamma rays. So the Vela pulsar's brilliant gamma-ray glow is a different kind of explosion. A continuous, contained detonation, a storm of light powered by the relentless spin of a dead star, reminding us that a star's death can be an ongoing spectacle of pure power. Some of the most fleeting cosmic fireworks last just a single millisecond. Fast radio bursts are incredibly brief flashes of radio waves that travel across billions of light years to reach our telescopes. In that thousandth of a second, an FRB can release as much energy as the sun emits over 3 entire days. The sheer power and brevity of these signals point to an origin of almost unimaginable density and violence. The leading suspect for at least some of these bursts is the magnetar, that same class of ultramagnetic neutron star capable of starquakes. A sudden rearrangement of its crust could launch a blast of radio waves into the cosmos. Other theories are more exotic, involving the cataclysmic mergers of neutron stars or the violent interactions of black holes with their surroundings. For a brief time, the most speculative idea was that these perfectly natural, yet seemingly artificial, pulses could be engineered signals from an advanced alien civilization. While this is no longer considered a likely explanation, the fact that it was ever a serious point of discussion highlights just how puzzling these signals were. The mystery deepened when astronomers discovered that not all FRBs are the same. Some are one-off events, a single, brilliant shout in the dark that is never heard again. Others, however, are repeaters. The same patch of sky will light up again and again with these millisecond flashes, sometimes in a predictable pattern, sometimes at random. This fundamental difference suggests there may be at least two distinct engines powering these bursts. A one-off event could be the final, catastrophic death cry of an object, like a neutron star collapsing into a black hole. A repeater, however, must involve a source that can survive its own outburst, like a magnetar that cracks under pressure but does not shatter. Each new detection adds another piece to this cosmic puzzle, proving that the universe holds secrets of energy and power on scales we are only beginning to perceive. The puzzle of fast radio bursts demanded a location, an address in the cosmos for these brilliant, fleeting flashes. For years, every attempt to pinpoint a burst's origin failed, leaving astronomers with a profound mystery and no home for the phenomenon. Then came FRB 121102. This was not a one-time event. It erupted again and again, a celestial alarm clock that refused to be silenced. Its repeating nature was the crucial clue that finally allowed the immense radio telescope arrays at the Very Large Array in New Mexico to catch it in the act and trace its signal with precision. The result was a cosmic landmark. FRB 121102 was not in our galactic backyard. It was traced back to a tiny, faint dwarf galaxy more than 3 billion light-years away. This single measurement changed everything. The vast distance confirmed that these millisecond flashes were unbelievably energetic, but more importantly, the location itself was a revelation. This was not a random spot in a giant spiral galaxy like our Milky Way. The burst originated from a region of intense star formation within this small, unassuming dwarf galaxy. This environmental clue was the key that ruled out models involving the one-time destruction of an object like a neutron star merger. Such cataclysmic events would not repeat, and they would not preferentially occur in such a specific, active stellar nursery. The evidence pointed powerfully toward a source that could survive its own outburst, a young, hyperactive magnetar. This incredibly magnetic neutron star, born from the recent explosion of a massive star in that stellar factory, could produce multiple bursts through repeated starquakes or through its powerful winds interacting with a dense cloud of surrounding material. FRB 121102 taught us that these brilliant radio flashes are not just random accidents, but messages from extreme objects thriving in uniquely energetic environments, a new window into the lives of the universe's most volatile stellar corpses. That landmark detection of a repeating fast radio burst proved we could find the source of cosmic explosions. But the single most important supernova in modern astronomy gave us more than just a location. It gave us a front-row seat to stellar death. Supernova 1987 erupted in the Large Magellanic Cloud, a small satellite galaxy of our own Milky Way, a mere 168,000 light-years away. This was the closest observed supernova in nearly 400 years, visible to the naked eye in the southern hemisphere. For astronomers, it was a once-in-a-lifetime event. For the first time, we had modern telescopes and detectors trained on a star before it exploded. We knew the progenitor star, a blue supergiant named Sanjalik -69 degrees 202. Its explosion confirmed a central pillar of stellar theory. The light curve, the way its brightness evolved over time, matched the predictions for a core collapse supernova almost perfectly. But the most profound evidence arrived not as light but as ghostly particles. Just hours before the visible light from the explosion reached Earth, underground detectors in Japan and the United States recorded a pulse of 24 neutrinos. These nearly massless particles, forged in the very heart of the collapsing core, had slipped effortlessly through the outer layers of the dying star and raced across space, arriving just ahead of the shockwave. This was the birth of neutrino astronomy. It was direct physical proof that the core collapse model was correct, that a neutron star had indeed formed in that initial cataclysm. Supernova 1987 was not just a spectacular light show, it was a textbook written across the sky, its pages filled with light, particles, and the final secrets of a star's death. One of the most famous cosmic explosions was first seen not with a telescope but with the naked eye. In July of the year 1054, Chinese court astronomers looked up and saw a new star blazing in the constellation of Taurus. They called it a guest star, a brilliant point of light that suddenly outshone every other object in the night sky, even visible during the daytime for 23 consecutive days. This celestial visitor was so striking that records of it appear in other cultures, from Japanese diaries to possible Native American rock art. Then, after glowing brightly for nearly 2 years, it simply faded from view. For centuries, that was the end of the story, a forgotten mystery in ancient texts, but the universe had not finished its work. Nearly 700 years later, in the 1700s, astronomers using early telescopes pointed at that same patch of sky and found not a star but a faint, fuzzy smudge of light. They called it the Crab Nebula, though they had no idea what it was. The connection was not made until the 20th century, when we finally understood the life cycle of stars. We realized that the ancient guest star of 1054 was a supernova, and the Crab Nebula was its expanding corpse, the beautiful, tangled wreckage still flying outward from that titanic blast. Today, we can study this remnant in incredible detail. The entire nebula is a vast cloud of gas and dust, a cosmic tapestry woven from the guts of that exploded star, and it is still expanding at over 1,000 kilometers per second. At its very center lies the final proof of the supernova theory, the crushed core of the original star. It is a pulsar, a neutron star spinning 30 times every second, blasting out pulses of radiation that illuminate the surrounding nebula, making it glow. The Crab Nebula is more than just a beautiful object. It is a direct link across time, a celestial crime scene where we can match the historical record of the explosion to the physical evidence it left behind, confirming our understanding of stellar death in the most poetic way possible. Our atmosphere is constantly under a silent, invisible barrage. Every second, high-energy particles from deep space strike the outer layers of our air, a rain of atomic shrapnel known as cosmic rays. These are not rays of light, but mostly protons, the nuclei of hydrogen atoms, along with heavier atomic nuclei, all traveling at nearly the speed of light. They carry so much energy that a single one can possess the kinetic force of a professionally thrown baseball, all packed into a subatomic particle smaller than an atom. For over a century, the source of these ultra-fast particles was one of astronomy's great puzzles. Where in the universe could nature build such a powerful cannon? The answer lies in the aftermath of the explosions we have been exploring. Supernova remnants, those expanding clouds of stellar debris, are now considered the universe's primary particle accelerators. The shockwave from the explosion, still plowing outward at thousands of kilometers per second, acts like a colossal and relentless magnetic piston. When a stray proton or atomic nucleus gets caught in this wave, it is bounced back and forth by turbulent magnetic fields trapped within the shock. With each crossing, the particle gains more speed, much like a tennis ball being volleyed between two approaching rackets. Over hundreds or thousands of years, This natural process accelerates particles to energies that dwarf the capabilities of our most powerful human-built machine, the Large Hadron Collider. These cosmic bullets are then flung out into the galaxy, some eventually finding their way to Earth, where they serve as a permanent, physical reminder of the violent stellar deaths that continue to shape our cosmic environment. That relentless search for cosmic signals occasionally delivers a mystery that stands alone. In August 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the sky. The data was printed out on a simple line printer, and a few days later, a volunteer named Jerry Amon was reviewing the readouts. His eyes fell upon a sequence of letters and numbers that made him stop. He circled it and wrote a single, powerful word in the margin: "Wow." The signal was a 35-second burst of intense, narrowband radio waves, exactly the kind of signature theorists predicted an artificial, extraterrestrial transmission might have. It came from the direction of the constellation Sagittarius, and it was over 30 times stronger than the background noise of space, but then it vanished. The Big Ear telescope never heard it again, and despite numerous targeted searches over the decades, the wow signal has never been repeated. It was a one-off event, a shout in the dark with no echo. This single, unexplained burst forces us to confront a humbling truth. For all our classifications of supernova and gamma-ray bursts, the cosmos is still capable of producing energetic events that defy our current understanding. It might have been a natural phenomenon we have not yet identified, perhaps a completely new type of stellar outburst or a bizarre interaction between a comet and the solar wind. Or it remains the most tantalizing, unconfirmed candidate for a signal from another intelligence. The wow signal is a permanent monument to the gaps in our knowledge, a reminder that some of the universe's most powerful messages are still waiting for their Rosetta Stone. These ancient stellar explosions did more than forge new elements. They fundamentally changed the structure of the cosmos itself. In the universe's earliest days, space was not the transparent void we see today. It was filled with a thick, obscuring fog of neutral hydrogen gas. The very first stars and galaxies, colossal and short-lived, began to blaze within this murk. Their lives ended in spectacular supernova, but it was their brilliant ultraviolet light during their brief lives and the intense radiation from the hot gas left after their explosions that truly reshaped the universe. This radiation was so powerful it blasted electrons away from the hydrogen atoms, ionizing them and burning away the primordial fog in a pivotal cosmic event known as the Epoch of Reionization. Think of it as a great cosmic dawn, not from a single sunrise, but from billions of stellar flashbulbs popping all across the young cosmos. This process, driven by the first generations of cosmic explosions, cleared the haze and made the universe transparent to light for the very first time. It was these initial, violent deaths that literally switched on the lights, allowing the clear, dark space between galaxies to exist and enabling the universe we now observe to come into view. These stellar explosions shape galaxies, but they too are subject to the universe's ultimate destiny. Our cosmos is not a static stage, but a system with a finite lifespan, and its final fate hinges on a mysterious force known as dark energy. This invisible pressure is causing the expansion of the universe to accelerate, and its ultimate strength will determine how everything ends. One possibility is a gradual, silent fading known as the heat death. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate. Over trillions of years, stars will burn out one by one, their fuel exhausted. Black holes will slowly evaporate through a quantum process called Hawking radiation. The universe will grow unimaginably cold and dark, with all energy evenly spread out. No more temperature differences will exist, meaning no work can be done, no stars can form, and no life can possibly exist. It is the ultimate state of maximum entropy, a cosmic equilibrium where all activity grinds to a permanent halt in the cold and the dark. But there is another, far more violent alternative, the Big Rip. This theory suggests that dark energy is not constant but grows stronger over time. If this phantom energy, as it is called, becomes dominant, the acceleration of the universe's expansion would not just continue, it would become infinite. First, galaxy clusters would be torn apart. Then, individual galaxies would be shredded. As the end nears, the phantom force would rip stars from their planetary systems. In the final minutes, planets and stars themselves would be pulled apart. In the last terrifying fraction of a second, the overwhelming force would overcome the very bonds holding atoms together, tearing every nucleus and every particle away from every other. The fabric of space-time itself would be ripped to shreds in a final, catastrophic, and universal explosion of nothingness. So, will our cosmos end with a silent, frozen whisper, or with a single, definitive, and violent bang that dismantles reality itself? The answer lies in the still unknown nature of the dark energy that fills the void. That number, 1.4, is a line drawn in the sand by the universe itself. It is the Chandrasekhar limit, the maximum possible mass for a stable white dwarf star. This seemingly simple value, roughly 1 4/10 times the mass of our Sun, is a fundamental boundary between a quiet stellar afterlife and a cataclysmic detonation. Its discovery is a story of youthful brilliance. A 19-year-old Indian physicist named Subramanian Chandrasekhar was traveling by ship to England for graduate studies in 1930. During the voyage, he pondered the ultimate fate of stars. He combined the new theories of relativity with the quantum nature of matter, and his calculations revealed something startling. He realized that a white dwarf, a star supported only by the quantum pressure of its electrons, could not exist above a specific mass. If the star's mass exceeded this limit, the force of gravity would overwhelm that quantum pressure, leading to a catastrophic collapse. At the time, this idea was controversial, even opposed by renowned astronomers like Sir Arthur Eddington, who found the implications unsettling, but Chandrasekhar was proven right. This limit is the key to one of the most important explosions in the cosmos. A white dwarf in a binary system, like the one in RS Ophiuchi, slowly steals mass from its companion. It is a patient stellar thief, inching closer to that 1.4 solar mass threshold. The moment it crosses the Chandrasekhar limit, everything changes. The star can no longer support its own weight. The increased pressure and temperature ignite carbon fusion in its core, but this time the fusion is not a steady process. It becomes a runaway thermonuclear inferno that rips through the entire star in a matter of seconds. There is no shockwave rebounding from a core, no neutron star left behind. The white dwarf is completely obliterated in a Type Ia supernova, a blast of such consistent power that it serves as a standard candle for measuring the vast scales of the universe. So this one number, discovered by a teenager on a long sea voyage, governs the fate of countless stellar corpses and lights the way for our exploration of the cosmos. Just as white dwarfs have their breaking point, neutron stars possess their own ultimate boundary. This is the Oppenheimer-Volkoff limit, the maximum mass a neutron star can possibly bear before its own gravity wins the final battle. While the Chandrasekhar limit is a sharp 1.4 solar masses, the Oppenheimer-Volkoff limit is a fuzzier value, estimated to lie somewhere between 2 and 3 times the mass of our Sun. This is not a clean line because it depends on the complex and still mysterious equation of state for neutron star matter. We do not know exactly how this ultra-dense material behaves under such extreme pressure. Is it a perfect fluid of neutrons, or does it contain strange particles like hyperons or even free quarks? The precise physics determines how much outward pressure the star can muster to fight the relentless crush of its own weight. The moment a neutron star's mass crosses this critical threshold, perhaps by accreting more material from a companion star or by merging with another neutron star, its fate is sealed. The degeneracy pressure of the neutrons, that final quantum mechanical stand against collapse, suddenly fails. There is no longer any force in the known universe that can hold it up. In a final, silent plunge, the entire star collapses inward, vanishing behind an event horizon to become a black hole. This limit is the ultimate cosmic cliffhanger, the invisible line separating a visible, spinning stellar corpse from the absolute darkness of a gravitational prison. The silent, cold void of space is now filled with a new kind of sight. The James Webb Space Telescope, with its golden eye, sees the cosmos in a way we never could before, piercing through the veils of dust that have long hidden the universe's most violent secrets. Where the Hubble Space Telescope showed us the beautiful, expanding shells of supernova remnants, James Webb peers directly into their fiery hearts. It analyzes the chemical fingerprints in the debris with a precision that is like moving from a blurry photograph to a detailed laboratory analysis. We can now see the exact elements forged in those final, cataclysmic seconds, mapping the distribution of carbon, oxygen, and iron across the wreckage. This tells us not just how a star died, but how it lived, what it was made of, and how efficiently it scattered the building blocks of planets and life back into the galaxy. But its vision stretches even further across time itself. James Webb is a time machine looking back to the era of the very first stars. These primordial giants were behemoths, hundreds of times the mass of our Sun, and their deaths must have been pure instability supernova of unimaginable power. They exploded in a universe still cloaked in primordial gas, and their light has been stretched into the infrared by the expansion of the cosmos. This is the light James Webb was built to capture. It is now hunting for the signatures of those first explosions, the ones that initially seeded the early universe with heavy elements and began the process of cosmic evolution that led to us. Every new image, every spectrum, is rewriting our textbooks on stellar life and death, revealing that the universe's energetic explosions are even more varied and complex than we ever dreamed. What other secrets will we uncover as we stare deeper into the cosmic forge? This new era of discovery requires a telescope that can watch the entire sky at once. The Vera C. Rubin Observatory, poised to begin operations in Chile, is that instrument. Its mission is nothing short of revolutionary: to conduct a 10-year-long movie of the southern sky called the Legacy Survey of Space and Time. Night after night, its enormous 3.2 billion pixel camera will capture the cosmos, revealing changes both subtle and spectacular. This relentless scanning will transform our study of cosmic explosions from catching rare, isolated events to monitoring a constant, dynamic celestial tapestry. The observatory is expected to identify an astonishing 20 million supernova over its decade of work. More importantly, it will catch these stellar deaths in their infancy, often within hours of their first light. This early detection is crucial, like arriving at the scene of a crime as it happens rather than finding the aftermath days later. We will see the first shockwaves breaking through a star's surface and track the evolution of the blast in unprecedented detail. But its vision extends beyond supernova. The survey's sensitivity and speed make it the perfect tool for hunting the faint, fleeting glows of kilonovae, those cosmic gold forges. By spotting these mergers quickly, it can alert other telescopes worldwide to swing into action, creating a global network of eyes to study a single event in every wavelength of light. The Vera Rubin Observatory will not just find new explosions, it will illuminate the entire life cycle of stellar violence, from the first spark to the final, fading echo. These stellar explosions are the architects of galaxies themselves. A supernova does not merely destroy a star, it sends a powerful regulatory message throughout its entire galactic neighborhood. This process is known as supernova feedback, a cosmic cycle of death and rebirth that governs the growth of galaxies. When a supernova erupts, it does not just vanish. It carves out a vast bubble in the surrounding interstellar gas, blowing it away with a powerful, hot wind. This sweeping action has two profound consequences. First, it clears away the raw fuel for new stars. By pushing this gas outward, the explosion effectively puts a brake on star formation in its immediate vicinity. It prevents a galaxy from burning through all its gas in a single, frantic burst of stellar birth. Without this feedback, galaxies would form stars with reckless abandon, quickly exhausting their fuel and leaving behind a stagnant, aging system. Second, the explosion does something even more vital. It seeds that cleared space with the heavy elements forged in the star's heart and during its violent death. Iron, oxygen, silicon, and gold are all churned into the galactic mix. This enriched material, when it eventually collapses to form new stars and planets, already contains the essential ingredients for rocky worlds and potentially life. So a supernova is not just an end. It is a galactic regulator, a recycling plant, and a fertilizing agent all in one. Its death ensures that future generations of stars will be born with a richer heritage in a galaxy whose structure and pace of life are shaped by these magnificent recurring explosions. Finding the star before it explodes is one of astronomy's greatest detective missions. We scan the heavens for telltale signs of a stellar ticking clock, a giant on the verge of collapse. These are supernova progenitors, and identifying them would give us a front-row seat to stellar death from the very first second. The most famous candidate is Betelgeuse, the red giant star in Orion's shoulder. It has been behaving erratically, dimming dramatically several times in recent years. This is likely caused by immense clouds of dust condensing from its own cooling outer layers, a sign of a star in its final, unstable throes. While Betelgeuse may not explode for another 100,000 years, its antics show us what the prelude to a supernova can look like. Then there is Eta Carinii, a volatile hypergiant over 7,000 light-years away. In the 1840s, it underwent a massive eruption, becoming the second brightest star in the night sky for a time, yet it did not go supernova. It survived and now surrounds itself with the beautiful, expanding homunculus nebula, the debris from that earlier outburst. This star is a true powder keg, potentially weighing in at over 100 solar masses, and it could detonate as a hypernova at any moment in the cosmic scale of time. The ultimate goal is to catch one of these monsters in the act, to have our telescopes already pointed at it when the core finally gives way. A galactic supernova, one inside our own Milky Way, is a rare event happening only a few times per century. To witness its birth cry, to see the initial shockwave break through the stellar surface, would provide a treasure trove of data that would rewrite our understanding of stellar physics. We are watching the sky, waiting for a star to die, hoping to see the moment the universe forges a new cosmic legacy. Even a silent explosion has a rhythm we can hear. The vacuum of space carries no sound, but the data from a supernova tells a story that can be translated into music. Scientists use a process called day-sonification to make these cataclysms audible, turning the numbers and graphs of a stellar death into a symphony of violence. Imagine taking the light curve, the graph of a supernova's brightness over time, and mapping it to pitch and volume. The initial, unimaginably violent shock breakout, the moment the blast wave first rips through the star's surface, would be a sudden, deafening crack, a single percussive blast of pure noise. This would be followed by a rapid, soaring rise in pitch and intensity as the explosion reaches its peak brightness, a screaming crescendo that represents the star shining brighter than its entire galaxy. Then the long, slow fade as the expanding cloud of debris cools and dims would become a deep, rumbling drone that gradually softens into silence over many months. Different elements detected in the spectrum could be assigned unique musical tones, creating a shimmering, chaotic chord of forged metals. Listening to this sonic translation is not just a scientific exercise, it is a deeply human way to experience the raw, unfolding power of a stellar death, to feel the violence of the cosmos resonate in a way that light alone cannot convey. The very explosions that forge cosmic elements also illuminate the universe's final fate. For decades, cosmologists believed the universe's expansion, born from the Big Bang, was gradually slowing down under the relentless pull of gravity. The ultimate question was whether that expansion would eventually reverse in a big crunch or simply coast to a halt. To find the answer, they needed to measure the expansion rate across vast cosmic time, and for that, they needed a perfect ruler. Their tool became the thermonuclear death of white dwarf stars, the type I supernova. Because these supernova all explode at nearly the same critical mass, they all reach nearly the same intrinsic peak brightness. This consistency makes them perfect standard candles. By observing how bright these distant stellar explosions appeared from Earth, astronomers could calculate their true distance. Then, by measuring the redshift of their host galaxies, they could determine how much the universe had stretched since the light began its journey. Two independent teams spent the 1990s meticulously collecting data from these cosmic mileposts, expecting to confirm the gradual deceleration. Instead, they found the opposite. The most distant supernova were significantly fainter than predicted. This meant they were farther away than anyone had thought. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was overcoming gravity's grip on the largest scales, pushing galaxies apart at an ever-increasing rate. This discovery of cosmic acceleration was so shocking and profound it earned the Nobel Prize. We call that mysterious force dark energy. It is the dominant component of our universe, and its nature remains one of the greatest unsolved problems in physics. The violent, consistent death of stars revealed that the cosmos is not only expanding but flying apart. Its ultimate fate now tied to a shadow that we can only see by the light of stellar explosions. This cosmic violence is not random chaos but a delicate, necessary recipe. The specific energy of these explosions appears perfectly tuned to create a universe that can eventually support beings like us. Consider the fundamental elements of life, carbon and oxygen. They are forged in the hearts of stars and scattered by supernova, but the process requires a precise level of violence. If supernova were significantly weaker, these vital elements would not be flung far enough into space. They would fall back into the remnant neutron star or black hole, locked away forever. The cosmic gas clouds that form new stars and planets would be barren, lacking the chemistry for rocky worlds or complex molecules. On the other hand, if these explosions were too powerful, the consequences would be equally sterile. An overly energetic blast would shatter the newly forged atoms into a featureless soup of hydrogen and helium, destroying the very building blocks it created. The universe would remain a primordial desert. This fine-tuning leads to a profound philosophical idea known as the anthropic principle. It suggests that the physical constants and cosmic processes we observe must be compatible with the existence of conscious life because we are here to observe them. We see a universe with supernova of a certain strength because that specific strength is what made our existence possible. It is a cosmic selection effect. We are not just passive observers of these stellar cataclysms. We are a direct product of them, living proof that for billions of years, the universe has been exploding with just the right amount of force to eventually ask the question, why? Far out in the cosmic deep, tiny galaxies glow with an unearthly green light. Astronomers affectionately call them green peas, not for their shape, but for their color and small, compact size in telescope images. These are not serene islands of stars like our Milky Way. They are cosmic pressure cookers, realms of extreme and frantic star formation. Within their limited bounds, stars are being born at a rate hundreds of times faster than in our own galaxy. This frantic birth rate leads to an equally frantic death rate. Green pea galaxies are essentially supernova factories. Because their most massive stars live fast and die young, stellar explosions detonate with a ferocious, relentless frequency. Imagine a single small galaxy, no bigger than a mere speck in our sky, where a supernova might rip through the void not once a century but several times a year. This creates a continuous, churning feedback loop of violence and creation. The shock waves from one explosion compress nearby gas clouds, triggering the birth of the next generation of stars, which will themselves soon explode. This offers astronomers a unique laboratory. We can study the cumulative effect of dozens, even hundreds, of supernova going off in a relatively small volume over a short cosmic time. It is a chance to watch how these titanic blasts en masse heat interstellar gas, drive powerful galactic winds, and ultimately regulate the very growth of their tiny green home. Our own galaxy holds the fossil of a cataclysm, stretching 25,000 light-years above and below the galactic plane. Two colossal spheres of energy loom, invisible to our eyes but blazing in high-energy gamma rays. These are the Fermi bubbles, first discovered by the Fermi Gamma Ray Space Telescope, and they are the ghostly imprint of a past explosion of almost unimaginable scale. They are not made of stars or gas in the traditional sense, but are instead vast cavities filled with ultra-hot plasma and tangled magnetic fields, emitting some of the most energetic light in the cosmos. Their very existence points to a violent eruption from the heart of our Milky Way, a sudden and tremendous release of power that punched these bubbles out of the surrounding galactic halo. The prime suspect for this cosmic violence is our own galaxy's supermassive black hole, Sagittarius, a star. While it is quiet today, the evidence suggests that several million years ago, it awoke from its slumber in a spectacular fashion. It may have devoured a massive cloud of gas or even an entire star, and in the process, it unleashed twin jets of relativistic particles or a single, stupendous outflow of energy. This event, lasting perhaps for tens of thousands of years, would have flooded the galactic center with radiation and blown these enormous bubbles clear through the galaxy's diffuse outer atmosphere. We are living in the calm after that storm, gazing up at the lingering aftermath of an eruption that, for a brief cosmic moment, turned the center of our Milky Way into a quasar. These silent, glowing bubbles are a permanent reminder that even our own familiar galaxy is not immune to the universe's most energetic explosions. Deep within the dusty heart of our galaxy, a stellar black hole is performing a strange act of destruction and creation. Known to astronomers as 1E1740.7-2942, this object earned a far more dramatic nickname, the Great Annihilator. It is a microquasar, a stellar mass black hole perhaps 10 times heavier than our Sun, locked in a gravitational dance with a companion star. Like a miniature version of the quasars that power distant galaxies, the Great Annihilator is actively feeding, pulling gas from its neighbor into a superheated accretion disk. But its true claim to fame lies in what happens next. This system fires off powerful jets of particles, and one of these jets appears to be slamming directly into a dense cloud of molecular gas near the galactic center. The collision is one of the most fundamental in the universe. Within that cloud, the electrons being hurled out by the black hole meet their antimatter counterparts, positrons, which are also present in the jet or created in the violent impact. When an electron and a positron meet, they do not simply bounce apart. They annihilate each other in a flash of pure energy, transforming their combined mass directly into gamma-ray radiation with a very specific signature. This is the radiation of annihilation, a light born from the total destruction of matter. The Great Annihilator provides a stunningly clear laboratory, demonstrating how the chaotic environment around a small black hole can become a factory for some of the most exotic and energetic physics in the cosmos. Sometimes a stellar corpse does not rest in peace. It flees the scene of its own death at a breathtaking speed. Meet PSRB 2224+65, a pulsar astronomers have nicknamed the Cosmic Cannonball. This city-sized neutron star is hurtling through the galaxy at over 800 kilometers per second, fast enough to travel from Earth to the Moon in just under 10 minutes. Such an incredible velocity demands an equally violent explanation. The pulsar was almost certainly given a powerful kick by the supernova that created it. Not all stellar explosions are perfectly symmetrical. If the detonation is lopsided, if more neutrinos and debris are blasted out in one direction than another, the recoil can literally boot the newborn neutron star clear across the galaxy, like a rocket firing unevenly. The cosmic cannonball is a permanent fugitive, a direct product of that ancient asymmetrical blast. As it races through the void, it does not travel silently. Its immense speed forces it to plow through the thin gas that drifts between the stars. This is the interstellar medium, and the pulsar's passage is anything but gentle. Just as a speedboat creates a bow wave as it cuts through water, the pulsar creates a bow shock in this cosmic gas. The intense radiation and particle wind flowing from the pulsar itself slams into this interstellar material, compressing and heating it until it glows. From our vantage point, this glowing shockwave forms a shape that is both beautiful and strangely familiar. A long, narrow neck of energy leads to a bulbous body, creating an object known to astronomers as the Guitar Nebula. It is a celestial instrument strummed by the passage of a runaway star, a visible scar etched into the galaxy by one of the most powerful kicks the universe can deliver. A star can swell into a brilliant red giant only to be consumed by its own partner. This is the luminous red nova, an eruption that defies our usual categories of stellar death. It is not the core collapse of a single massive star, nor is it the surface detonation on a white dwarf. Instead, it is a slow, intimate, and spectacularly violent merger. Picture two stars locked in a gravitational embrace, one a bloated red giant and the other a smaller companion, perhaps a white dwarf or even another main sequence star. Over millennia, their orbits decay, drawing them closer and closer. Eventually, the smaller star plunges directly into the diffuse outer layers of the giant. Friction and tidal forces rip both stars apart, churning their material together into a single, hot, and turbulent common envelope. The energy from this cosmic collision does not escape immediately. It is trapped, heating the swirling mass of gas until the pressure becomes unbearable. Then, the star system violently ejects its outer layers in a brilliant, expanding shell of gas and dust. What makes this explosion so distinct is its color and its pace. A luminous red nova glows with a deep, crimson light, much redder than the white-hot blaze of a classic nova or supernova. This is because the ejected material is rich in cool molecules and dust that form rapidly in the expanding cloud, filtering out the blue light and leaving a dominant red glow. And unlike a supernova, which can fade in weeks, the light from a stellar merger can take months or even years to slowly dim, a long, lingering farewell from two stars that have become one. This is a different kind of creation through destruction, forging not a neutron star, but often a single, rejuvenated star from the ashes of two separate lives, a temporary beacon of red light in the cosmos marking a final, unifying embrace. Some stars burn so fiercely they strip themselves bare before their final death. Wolf-Rayet stars are these cosmic powerhouses, massive suns caught in a desperate race against time. Born with over 20 times the mass of our own sun, they live life at a frantic, unsustainable pace. In just a few million years, they burn through their nuclear fuel, casting off their own outer layers in a continuous hurricane-force stellar wind. These are not gentle breezes, they are supersonic outflows blasting material into space at speeds exceeding 10,000 kilometers per second. This relentless self-stripping peels the star back to its core, exposing the heavy elements forged deep within its heart. A Wolf-Rayet star is a stellar onion peeled down to its final, incandescent layers, shining with a brilliance that reveals the products of advanced nuclear fusion, like helium, carbon, and oxygen, directly to our telescopes. This process sculpts its surroundings into some of the most beautiful and complex structures in the galaxy, vast, glowing nebulae that look like cosmic pinwheels or delicate rings, all forged from the star's own expelled atmosphere. But this beauty is a warning sign. A Wolf-Rayet star is a pre-supernova time bomb, ticking down the moments until its core can no longer support its own weight. It has already done the work of a supernova in slow motion by violently seeding its neighborhood with enriched material. All that remains is the final, core-deep collapse, the trigger for one of the universe's most energetic explosions, a grand finale that has been meticulously prepared by the star's own spectacular self-destruction. In October 2022, our planet was silently struck by a wave of radiation so powerful it blinded the very instruments designed to detect it. This was gamma-ray burst GRB 221009A, an event astronomers quickly nicknamed the boat the brightest of all time. For over 10 minutes, this single event flooded our gamma-ray satellites with more photons than any burst in recorded history. The initial flash was so intense it saturated most detectors, creating a scrambled mess of data that required brilliant forensic work to untangle. But the show was far from over. The afterglow of the boat lingered for weeks, a fading ember that remained visible across the entire electromagnetic spectrum, from radio waves to the highest energy gamma rays. This incredible persistence gave astronomers an unprecedented opportunity to study the anatomy of a hypernova in exquisite detail. The data paints a picture of a truly monstrous stellar collapse, likely a star dozens of times more massive than our Sun, whose direct collapse into a black hole generated a pair of relativistic jets of unmatched power and precision. The boat is not just a new record holder, it is a Rosetta Stone for extreme physics, offering clues about the composition of these jets, the nature of the material they plow through, and the inner workings of the cosmic engine that can launch them. An event of this magnitude is thought to occur only once every 10,000 years, making our detection of it a moment of incredible cosmic fortune. We are still unraveling its secrets, learning what it means when the universe unleashes its absolute brightest flash upon the darkness. Our current catalogue of cosmic explosions is about to be rewritten. The next decade will transform astronomy from a spectator of light into a listener of the universe's full symphony. We are entering the mature era of multi-messenger astronomy, where we will not only see these cataclysms, but also feel the space-time shake and catch the ghostly particles they emit. It begins with a new sense for gravitational waves. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will launch in the 2030s. Instead of kilometer-long tunnels on Earth, LISA will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart, connected by lasers. This vast instrument will be sensitive to low-frequency ripples in spacetime that ground-based detectors cannot hear. It will catch the faint, rising chirp of supermassive black holes merging at the hearts of galaxies and feel the gentle hum of binary white dwarfs spiraling together for eons. But most importantly for our story, it could detect the gravitational rumbling from within a supernova itself, feeling the chaotic churn of matter in the seconds before the core collapses, a direct probe into the very heart of a dying star. At the same time, next-generation neutrino observatories like IceCube Gen 2 will expand our particle vision. Buried even deeper in the Antarctic ice, its thousands of sensors will act as a gigantic net for these elusive messengers. When the next galactic supernova occurs, it will not capture a couple dozen neutrinos, as with supernova 1987A, but many thousands. By analyzing the precise timing and energy of this neutrino flood, we can effectively create a real-time ultrasound of the collapsing stellar core, watching as it first forms a neutron star and perhaps even witnessing the exact moment it collapses further into a black hole. Finally, a new fleet of space telescopes, from the recently launched James Webb to future X-ray observatories, will be standing by. The gravitational wave signal from LISA will provide the direction. The neutrino pulse from IceCube will give us the precise moment of collapse, and the telescopes will then zoom in to capture the resulting fireball across every wavelength of light. This coordinated alert system will allow us to witness the birth of a black hole or a magnetar from its very first microsecond. We will see not just the aftermath, but the engine itself. This is the ultimate goal, to move from observing the brilliant funeral pyre to understanding the precise spark that lit the match. What fundamental secrets of matter and energy will we uncover when we can finally observe a cosmic explosion with every sense the universe allows? Your computer screen could be the next frontier for discovering a stellar explosion. The hunt for supernova and other fleeting cosmic events is no longer confined to professional astronomers on remote mountaintops. Today, a global army of amateur astronomers and citizen scientists is making vital contributions, spotting these brilliant flashes from their backyards and even their living rooms. Amateurs have an incredible advantage: their tireless dedication. They know the night sky intimately, and by taking repeated images of galaxies, they can spot the tiny, new pinprick of light that signals a star's death. Many of these discoveries are formally reported to the International Astronomical Union, with credit given to the sharp-eyed individual who first spotted the cosmic fire. But you do not even need a telescope to join this hunt. Online platforms like Zooniverse host projects where anyone can help science. You might be presented with images from robotic sky surveys and asked to compare new and old pictures of the same galaxy, looking for that one new bright spot. It is a cosmic version of Spot the Difference, and a click of your mouse could flag a potential supernova for professional follow-up. This is not busy work. Volunteers have discovered entirely new classes of objects and identified thousands of candidate explosions, processing a volume of data that would overwhelm any single research team. This collective effort proves that the wonder of cosmic discovery belongs to everyone. The next great explosion lighting up a distant galaxy might not be found by a giant telescope first, but by a teacher, a student, or a retiree simply looking at the sky with curiosity. These titanic blasts are the universe's dual nature, a beautiful and violent cycle of creation and destruction. We have journeyed from the stellar death cries of supernova to the focused, relativistic blades of gamma-ray bursts. We have felt space-time tremble from colliding neutron stars, forges where the gold in a wedding ring is born, and witnessed the strange, repeating pulses of magnetars and fast radio bursts. Each explosion, from a humble nova to a hypernova, plays a distinct and vital role. They are not merely cosmic accidents. They are the architects of reality, the engines that forge the elements of life, the regulators that control the birth of stars in galaxies, and the mysterious signals that continue to challenge our understanding of physics itself. The next time you gaze at the night sky, remember you are looking at a dynamic and ever-changing arena. Those points of light are born from ancient explosions, and their eventual deaths will seed future worlds. We are all quite literally children of these cosmic cataclysms. Tell us in the comments which of these 50 facts reshaped your view of the universe.